Hello, welcome to this new lecture of the course Transportation Network Analysis. So, in the last class we were discussing about Probit based loading, so we will be continuing in that direction. So, just to recall, so what we do in every iteration of this algorithm is that we sample the link travel times from the distribution of the perceived link travel time distributions. Okay. So, if you remember, we assume that in every link we have a normal distribution of the perceived travel time here. So, these are distributions of the perceived link travel times. Okay. So, from each of these distributions, so we pick one value. So, we pick one value, suppose this comes out to be 1, this comes out to be suppose 2, this value has come out to be 2 again, this suppose 3, and suppose this is 4. Okay. So, we determine that with these link travel times that we have got, what is the shortest path for every OD pair, and then we do all or nothing assignment. So, we assign all the flow to that path for every OD pair which is the shortest. Okay. So, in this example the topmost path is the shortest. So, we assign all the flow to that path. Okay. And just to tell you one more thing, so since these link travel times are assumed to have normal distribution, the perceived travel time for every path will also have normal distribution, because it arises from the property that the sum of various normal distributions also turn out to be normal distribution. Okay. So, this kind of discussion is provided in detail in this Sheffy's book. So, for our purposes we just need to know that these different link travel times, perceived travel times have normal distribution. Okay. Okay. So, one thing is that when do we decide to stop? So, we can decide to stop when we observe that the variance of the average link flows is not changing that significantly. Okay. So, suppose for every link we will be getting a value of the perceived travel time in each iteration. Okay. And suppose after the end of every iteration we are determining what is the average link travel time for every link. Okay. So, when we realize that this average link travel times distribution, if we again plot that, its variance is not changing that much. So, then we can decide that no further iterations of this Monte Carlo simulation should be done. Okay. So, but before doing this we need to specify in the beginning itself that what is that threshold at which we will be deciding to stop, that is when we will be deciding that the variance of the link travel time values becomes lower. Okay. So, that threshold values that need to be decided beforehand. Okay. So, once this variance becomes lower than a given value, we stop. Okay. So, again just to help you understand, suppose for a particular link, I mean these are the values that we got 1, 5 and 10 from the distributions of the perceived travel time for. Okay. And suppose we only did 3 iterations. Okay. So, then this is what we got. Now, this is the average value. Now, we can also determine the variance across these 3 values that we got, that will be something. Okay. So, when this variance turns out to be something smaller, as we will be doing more and more iterations, there will be some more values here. Suppose it turns out to be 6, then 3 and so on. So, when do we decide to stop? So, when this variance becomes less than some predefined quantity, then we stop. Okay. And this has to happen for all of the links and so on. Okay. This was just for a particular link. So, note that the Probit loading model does not suffer from the limitations faced by the logit model, as the Probit does not make assumptions such as identically distributed error terms. Okay. So, Probit model, since it allows the error terms to have correlation across the alternatives, they need not come from the same distribution and so on. So, therefore, it is not suffering from the limitations which the logit model suffers. Okay. So, if you remember in the Probit model, we assume that the error terms are coming from a joint distribution of the normal distribution. Okay. So, for example, if it is a two alternative case. So then the error distribution is kind of a bell shaped normal distribution in 2 dimensions. Okay. So if you have to pick the error values, like that is if you have to suppose sample these error values, so we will be picking one point randomly in this 2 dimensional normal distribution. Okay. And whatever point that we pick, it will have two coordinates. One coordinate will be corresponding to the error value of the first alternative, and the second corresponding to the error term of the second alternative. Okay. So these two error values that we will be getting, they will be connected to each other because they are connected to what point we chose. Okay. They are not coming out independently. Okay. And also the variance of one of these error terms need not be exactly be the same. Okay. So for example, if it's a bell shaped curve in 2 dimensions, the variance in one dimension need not be exactly be the same as the variance in the other dimension. Okay. So those kind of limitations that the logit suffers are not there in Probit, but still for our discussion here we will be using the logit modeling only, because this logit based loading has a closed form expressions for determining the choice probabilities. Okay, which is not the case for this Probit based loading, because we have to resort to doing this Monte Carlo simulation, which is not having an analytical expression. Okay. And why is this Monte Carlo simulation always required for the case of Probit loading, whether we have to determine the choice probabilities or the satisfaction function and so on? Because the cumulative distribution function of a normal distribution is not having closed form expression. Okay. So those values are given in some standard tables and so on, which themselves are coming from numerical integration and so on. Okay. So now we will be coming to some ending remarks here. So until now we have focused on the formulation and solution of stochastic network loading models. Okay. We saw different kind of network loading models, the logit based loading model, then the Probit based loading model. And these models assign a set of OD trips to a transportation network in which the link travel times are stochastic but fixed. That is, they are not flow dependent. Okay. So although we allow the link travel times to be random in these cases, but we do not assume that these travel times will be a function of the flow. Okay. So therefore we have not taken that aspect into account, and as you remember, we had mentioned this before, that this aspect of the dependence of the flow on travel time, so this will be brought later. Okay. So until that is brought, this equilibrium dimension does not come into picture. Why? Because even if you look at the deterministic case, when we had the deterministic user equilibrium, so there also we had seen the equilibrium situation. Why? Because the travel time used to increase as the flow on a link used to increase. Okay. So if the travel time, for example, was constant, then there is no need of equilibrium situation, because then every person who is going from an origin to destination will want to prefer the shortest path, because even if everyone decides to take the shortest path, the travel time of that path will not increase. Okay. So that we usually do in the all or nothing assignment, but that step does not take into account that this travel time is also a function of the flow. Okay. So that's why there is a separate step in the convex combination of this user equilibrium that takes into account the relationship between the travel time and the flow. Okay. So these stochastic network loading models are only the extensions of this all or nothing assignment. Okay. So they are the same, just that the travel times are now assumed to be random, but still we have not considered the dependence of flow on the travel time. Okay. So now we will be introducing this equilibrium dimension into the problem. Okay. So now we will be assuming that the flow will affect the travel times. So now the perceived travel times will model to be not only as random variables, but they will also be flow dependent. Okay. So let us come to this discussion of stochastic user equilibrium. Again, all of this discussion is available in Joseph Shappi's book on urban transportation networks. So, here it will be assumed that the mean travel time of each link is a function of the flow on that link. So, see, the perceived travel time of each link is assumed to be random in this stochastic setting, right? But now the travel time has also get connected to the flow. Now, if there is a distribution that is associated, for example, with the perceived travel time of a link, so then what value from this distribution should we attach it with the flow? Because there are multiple such values in the distribution. Okay, so if we say that the travel time should increase as the flow increases, so what do we actually mean by that? I mean, what does a distribution increasing means with the flow? That has no direct meaning. Okay, so that is why what we are trying to say here is that whatever the mean of this distribution is, suppose this is the mean, this value will be function of the flow on that link. So if the flow increases, this mean will increase, and that will automatically shift the distribution on the right side. Okay, so that is how we are trying to connect the distribution of the perceived travel time on each link with the flow on that link. Okay, so let this Txa be the link performance function of a link A. Okay, so this kind of notation we have seen before, and in short we will be representing this by Ta. Okay, so this above assumption then means that the expected perceived travel time on link A, which is given by this, is a function of this Ta, which is a function of the flow. That is, for example, if for link A this Taxa is suppose 1 plus 2xa square. Okay, so we are saying that the perceived travel time which is given by Ta, and then we take the expected value of that. The expected value of the perceived travel time on link A will be equal to 1 plus 2xa square. That is, the expected value of this perceived travel time on this link will be a function of the flow on that link. Okay. Now, the inputs to this stochastic user equilibrium problem will be the same, in the sense that now also we will be having the travel demand, that is QRS values between every origin R destination S will be given to us. Okay. So then the stochastic user equilibrium conditions can be characterized by the following equations. That is, the flow on path K connecting R to S is equal to QRS times PKRS, where QRS is the demand from R to S and PKRS is the probability of choosing the kth path from R to S. Okay. So this is what it is saying. PKRS is the probability that route K between R and S is chosen given a set of measured travel times T here. Okay. Now, if you remember, when we had the deterministic user equilibrium case, so there we had seen that the first order conditions of Beckmann's transformation are actually equivalent to the user equilibrium conditions. Okay, so there we had something like FKRS times this CKRS minus URS, this was equal to 0, and then we had CKRS minus URS greater than equal to 0, and then there were two other constraints that are come standard. Summation FKRS is equal to QRS for all RS, and then FKRS are greater than equal to 0 for all R, S and K. Okay. So mainly these two conditions are actually the important part of the user equilibrium condition. That is, we were saying that for every origin destination pair RS, we will be having two set of paths, that is one set of paths will be used and the other ones will be unused. So the used paths will be such that the travel time on those used paths will be equal, and it will be equal to the minimum travel time on any path connecting R to S, which will be URS. Okay. Whereas if the a path is unused from R to S, so then FKRS is 0, and then only thing we can say is that the travel time on this path connecting R to S will be greater than or equal to the travel time on any used path connecting R to S. Okay. So these conditions were the user equilibrium conditions. Okay. Now a counterpart of that is this here, that is this FKRS is equal to QRS times PKRS for all K, R and S. Okay. Now we will not be seeing how these conditions got derived. Okay. But if anyone is interested, one can look at this book by Yosef Sheffi on urban transportation networks. But let us kind of assume that these conditions actually give the conditions for stochastic user equilibrium. Okay. So we will also be seeing one example later, so that will give us some intuition behind these equations. Okay. And also it might not be very intuitive that since stochastic user equilibrium is an extension of the deterministic user equilibrium, so now we are having these travel times which are assumed to be random, whereas they were not assumed to be random before. So how do these conditions become more general than these ones? Okay. So if we assume, for example, that the randomness across the different paths is not there, so then these conditions should turn out to be these. Okay. So again, that kind of intuition is available in the book, but we will not be discussing that because there are various other important things to also discuss, and this involves a lot of derivation which might be out of the scope of this course as well. Okay. So this PKRS is the function of the major travel times here, which is denoted by this bold T here. Okay. So this is the probability that the perceived travel time on path K connecting R to S is the lowest among the perceived travel times across all the paths between R to S. So this is what it is saying here. Okay. Given the set of major travel times that we have. Okay. So here CKRS is a random variable representing the perceived travel time on route K between R and S. Okay. Therefore, the CKRS will be equal to the summation TA times delta AKRS. So TA is the perceived travel time on link K, and the way it is connected to the perceived travel time on path K connecting R to S is given by these equations. So again, these are similar to what we have seen before. So now these link travel times and the path travel times are connected by this parameter delta AKRS. So this is equal to 1 if link K is part of the kth path from R to S and 0 otherwise. So these values of delta AKRS can be derived from the network structure. Okay. Okay. So note that the following regular conditions also hold in equilibrium. So this is the first condition, that the expected perceived travel time, which is this of link K, will be equal to the travel time that arises by putting the flow values on link K. Okay. This is what we have seen before. Also, the sum of the paths flows on different paths here will be equal to the travel demand QRS, and the flow on any link K can be determined by the flows on different paths by this relationship. Okay. So again, delta AKRS is being used here to relate the link flows with the path flows. Also note that this condition, that the sum of the path flows across any origin to destination is equal to the travel demand, this is automatically satisfied if we know that the stochastic user equilibrium condition is given by this FKRS is equal to QRS times PKRS, okay, for all R, S and K. Why? Because we can check this. So when we put the summation on both the sides here across all the paths K here, so this is summation, okay, then you can take QRS outside here and then we get summation PKRS across all paths K here. So this summation PKRS is equal to 1, okay. So this will turn out to be QRS because the sum of the probabilities across all of these paths between any origin destination pair will be equal to 1, okay. That is coming from the standard definition of probability, okay. So if you are having different choices and you have to select one of these choices, then the sum of the probabilities across all of these choices will be equal to 1, okay. So that is how we get this relationship here, okay. So this condition FKRS is equal to QRS times PKRS for all K, R and S characterizes the stochastic user equilibrium condition, okay. So this is kind of the equivalent of what we had seen the first order conditions of Beckmann's transformation in deterministic user equilibrium, okay. Also one thing to emphasize is that if, for example, in some assignments or exams, if we just say user equilibrium, it will automatically mean the deterministic user equilibrium, okay. The simplest form of the deterministic user equilibrium or the user equilibrium that we have seen, okay. Only if we say stochastic user equilibrium, then it will mean the stochastic case, okay. Otherwise by default it will only imply the user equilibrium in the deterministic case that we have discussed before, okay. Now this stochastic user equilibrium case, no traveler can improve his or her perceived travel time by unilaterally changing routes, okay. So this is kind of an equivalent of the user equilibrium condition. There we used to say that no traveler can improve his or her own travel time by unilaterally changing routes, okay. Now we are saying that it is the perceived travel time that they cannot improve, okay. An intuition to think this is that, for example, and this is coming from this definition itself, is that suppose there are 1000 people who want to travel from origin R to destination S, okay, and suppose there are two paths connecting that. So for every traveler who will be making the choice, what he will be doing is that he will be picking one sample value of the perceived travel time of the first path. Suppose for him the values come out to be 10, and for the perceived travel time of the second path he gets the value of 20. So for him he has perceived the first path to be shorter, so he will be taking the first path. But suppose if the second traveler comes, he again randomly picks the perceived travel time path values from their respective distribution. So suppose for the first path he gets the perceived travel time value to be equal to say 15, whereas for the second path he gets to be equal to 10. So then for him the second path is shorter than the first one, so he will be choosing the second path, okay. So in this way these 1000 travelers will be making their own choice. For each of them they will be choosing that path which they perceive it to be the shortest, okay. And since these perceived travel times across these different paths are random variables, so it is not that one of the path will always have perceived travel time to be lower than the other. There is a probability with which the perceived travel time of the first path will be lower than the second and vice versa, okay. So for example, if the probability of that the first path will have lower perceived travel time value as compared to the second path, suppose that probability is equal to 0.4, and automatically the probability that the second path will be perceived to be having lower travel time will have 1 minus 0.4 equal to 0.6 probability, okay. So that means that if there are suppose 1000 people who want to go from this origin R to destination S and they have the choice of these two paths, so approximately 400 people will be choosing the first path and 600 people will be choosing the second path, okay. So this PKRS is equal to probability that the perceived travel time on path K connecting R to S is the lowest among the perceived travel time of all of these paths, okay. So the choice probability is the probability that the perceived travel time on the chosen route is the smallest of all the routes connecting OD pair under consideration, okay. So this is what I had just said. given the major travel time values. Okay. Now at the equilibrium, the measured travel time on all the used paths may not be equal. Okay, so this is just one thing to keep in mind. The measured travel time on all your used paths may not be equal. Okay, because people will be making the decisions based on the perceived travel times. Okay, some people might perceive this path to be shorter, or some might perceive that to be shorter. Okay, and based on that they will be making the decisions. Okay. Instead, the travel time will be such that this condition always holds. Okay. So, if this QRS is 1000 and the probability that the perceived travel time on the first path is less than the perceived travel time on the second path is suppose 0.4. So, then the flow on the first path connecting R to S will be 400, whereas the flow on the second path connecting R to S will be 1000 times the choice probability for that path, which is 0.6 equal to 600. Okay. And again, this is saying the same thing that I had said before, that the stochastic user equilibrium is a generalization of this deterministic user equilibrium case. Okay, that is, this user equilibrium, deterministic user equilibrium case is a special case of stochastic user equilibrium. Okay. So, when the variance of the travel time perception is 0, then stochastic user equilibrium is identical to the normal user equilibrium or the deterministic user equilibrium that we had seen before. Okay. And this variance is solely coming because of the variance of the error terms that we assume in the travel times. Okay. So, if variance of those error terms is 0, then anyway the perceived travel times will also be having 0 variance, that is, they will be deterministic because the major travel times are anyway deterministic. Okay. So, I will suggest that as these lectures move on, keep revisiting these topics, because these are slightly more complex as probabilities are involved. Okay. So, like the way we had this Beckmann's transformation, which was the optimization formulation for the deterministic user equilibrium case, this stochastic user equilibrium case can also be formulated as an optimization problem. Okay. So, this is the optimization problem here. So, there are 3 terms in the objective function, one is this, then the other is this, and the other is this. Okay. So, this looks slightly complicated here. Again, in the same way that the user equilibrium formulation for the deterministic case did not have any intuitive reason behind the objective function value, the same is here also. Okay. So, there is no intuitive way to understand this objective function, and the way this has come out is that if you write down the first order equations for this optimization problem, then it will turn out to be equal to these equations for stochastic user equilibrium, which is given by this that FKRS is equal to QRS times PKRS, okay, for all K, R and S. Okay. So, the first order conditions for this optimization problem will be this. Okay. So, just so that what optimization problem should be developed, so that you get these as the first order conditions. So, that is how this was developed most likely. Okay. And one thing to also notice is that there is only an objective function here, there are no constraints here. So, the reason is that at the optimal solution of this optimization problem, the constraints are automatically satisfied what we need. Okay. So, again, the proof behind that is not discussed here, but it is available in the standard reference if someone is interested. So, this is what it is saying: at the solution of this optimization program, the network constraints are satisfied, and thus the program can be minimized as an unconstrained optimization problem. So, the main constraint that we would be worried about, that whether it is satisfied or not, is that for every origin destination pair, the sum of the flows on all of the paths sum to the travel demand. Okay. This is an important constraint. This should be satisfied at the optimal solution of this. So the claim is that the optimal solution of this optimization problem will automatically be such that this kind of constraints are satisfied. Okay. And that was the reason actually that when, if you remember, when we had started solving the user equilibrium formulation using with convex combination algorithm, then the first step to determine the initial solution of this convex combination algorithm was to use all or nothing assignment. That is, we did not start with any link flows in the convex combination algorithm to solve the problem, because the link flows should be such that the sum of the path flows that are obtained from those link flows should sum to the travel demand of that OD pair that is given, and that should hold for every OD pair. Okay. So that is why we had not started with any arbitrary solution. We had started with the case that let us do the assignment of the flows using all or nothing assignment, and in the all or nothing assignment it is automatically ensured that the sum of the flows on all of the different paths connecting any OD pair should sum to the travel demand, because anyway we assign all of the travel demand for every OD pair to the path that is the shortest. Okay. So it automatically ensures that all of the flows that are summed across different paths equal to the travel time demand. Okay. So note that the first term of the objective function includes the expected perceived travel time function. Okay, as it's introduced in the discrete choice theory. So we kind of write this optimization problem for stochastic user equilibrium formulation in a slightly better looking way by replacing that expression with this in the first term here. Okay, where this is the expected perceived travel time, okay, for this OD pair RS. Okay, so this term was actually written in the previous slide here. So now we have replaced it with this. Okay. So with this we will be ending the discussion here, and then we will be continuing in the next class. Thank you.